And guess what, ladies and gentlemen? It is time for another installment of your favorite YouTube series, AP Statistics Special Problems. This one is Chapter 13. And let's take a look at it. Okay, airlines are always interested in weight. Weight is crucial because as they have more weight on the plane, it uses more fuel, and they have to make sure that they have enough fuel to make the trip. But they don't want to overload the plane with extra fuel because then again, that adds extra weight, burns more fuel. So wasteful and expensive. All right, so they keep careful tabs on how much weight the typical passenger brings onto a plane. And here we have a random sample. Notice it didn't say simple random sample. Some of us are still making that mistake. Remember, there's more than one type of random sampling, right? Stratified, systematic, simple, right? There's multiple types. So every time it says random sample, that doesn't necessarily mean simple random sample. And as a matter of fact, if you think about trying to sample airline passengers, it probably wasn't a simple random sample. I highly doubt they got a list of everyone who traveled cross-country and listed them all out and did a simple random sample. It's probably much more a systematic random sample where they just asked every 10th passenger or something along those lines, or weighed their luggage. Probably didn't even have to necessarily ask them, right? Okay, so, but a large sample size, and it was random. And here's the data they found. Okay, question A. Could distribution of trip durations be approximately normal? Now, this is a question that a lot of people miss. So if this is an AP exam question, tons and tons of students miss it. So stop and think for a second. Could they be approximately normal? Okay. Now, look at the data. The average trip length is 5 days. The standard deviation is 3 days. Okay. So if I try to go 2 standard deviations below the mean, right, that empirical rule, 2 standard deviations in either direction, 95% of the data, but notice I'm already into a negative trip length. That doesn't make sense, right? I can't have a negative trip length. The lowest I could have would be 0 days, but really that doesn't quite count. I mean, I guess I could fly a short flight and back, but it does say cross country, so not really possible. So really, I can only get a little over 1 standard deviation below the mean, and then it's cut off. So this has got to be kind of similar in a way to the chi-square distribution in that it gets cut off on the left side. So the answer, of course, no. This must be right skewed. Okay, as there is a lower cutoff, right? But no upper cutoff. So, you know, some people are going to take very long trips, so there's a long right tail here, but we don't have a left tail at all. It gets cut off at, 1 day or a half day or whatever it is. Okay, that was easy. Question B. What assumptions, conditions must be met in order to compute a 99% confidence interval for the mean trip duration? Okay. All right, so our conditions for a confidence interval on means. Okay, we need simple random samples. We need, well, I guess we may as well address it. Do we have a simple random sample? We're unsure here. But probably not. probably a systematic random sample, which should be safe. Right, because again, as long as we have good random data, it should be unbiased, so we should be safe. All right, let's see. We also need independence. Right, we shouldn't be asking the same passengers over and over and over again, right? We need independence. Well, that one's a little dicey as well, right? If we're asking single passengers, we should be fine. But if we're asking groups, right? If we're asking a travel group, a family, or you know, sporting team that's traveling across country and back, that would not be independent, and many people in the family or the sporting team, right? They're obviously going to have the same trip length. So we're a little unsure on here. So again, unsure. If we sampled random individuals or random groups, if groups were sampled, it could invalidate our results. Okay, and of course, the final requirement, we need normality. And again, here's the spot where a lot of students get tripped up, right? On letter A, we said trip durations, they're not normal. But if we're talking about now the mean trip duration with a sample size of 5,400 passengers, we now do have normality because the central limit theorem says the sampling distributions of sample means will be approximately normal when n is large enough, and 5,400 is certainly large enough. So we're good there. All right, so a sample of 5,400 will provide approximate normality of the sampling distribution of sample means due to the central limit theorem. Okay, and that's a biggie. There's going to be some questions on the AP exam that talk about the central limit theorem. As I've mentioned before, it's one of the big important concepts of our class. So it's important that you know when it applies, sampling distribution of sample means, and when it doesn't apply. Just, for example, trip durations. How are they distributed? Okay, we're not talking about the means here. We're just talking about all of them. So again, know when that applies and how it works. All right. Next question. Scatter plot of the data. Good thing they didn't ask us to enter 5,400 pieces of data and do it, right? We have a correlation of 0.57 between trip duration and weight of luggage. Okay. Suppose each passenger is given a 2-pound deli snack to carry onto the plane. Now everybody's total luggage weight will increase by 2 pounds. What effect will this have on the correlation coefficient? Okay. We actually discussed this quite a bit back in chapters 3 and 4, right? When we talked about linear transformation of data sets, and we said if we add a constant to every piece of data, it simply shifts the graph. It doesn't change the spacing, it doesn't change the correlation, it doesn't change spread. So the answer here is there will be no change. So adding 2 pounds to every, that's the key. If you didn't do it to everyone, then of course, yes, we would have a change, but to every person's luggage, will have no effect on the correlation. Okay, we'll simply shift the entire distribution 2 pounds to the right. All right, next one. Find the equation of the least square regression line for predicting luggage weight from trip duration. Okay, so luggage weight is our y variable, right? Our response. Trip duration is our x, our explanatory variable. And they want me to show my work. Okay. Let's grab a clean piece of paper. Okay, so scroll back here. This is the information we need in order to calculate our least squares regression equation. So you might recall, or if you forget, look on your formula sheet. That's why we have it. Okay. Our slope is equal to our correlation multiplied by the standard deviation of y over the standard deviation of x. Okay. And we have that information. So let's plug in. The correlation they told me was 0.57. And standard deviation of y. Let's see, we have here we are, standard deviation. We have 10 over 3. Okay, so weight of luggage x, duration of trip, I'm sorry, weight of luggage y, duration of trip x. So let's work that out. And we get 1.9. Okay, so there's our slope. All right, now we just need our y-intercept. And again, it's on the formula sheet if you forget it. You can just remember that every point goes through x bar, y bar, right? Or you can look on your formula sheet. So we have x bar and y bar given. X bar is, again, weight, and y bar, I'm sorry, I keep saying that backwards. X bar is duration, y bar is weight. Okay, so we have the point 5, 50. Okay, so we know we go through that point. We plug in. So 50, 1.9 times 5 plus a, and solving. So we get 40.5 as our y-intercept. And there we go. We now have our equation. 1.9 is our slope. 40.5 is our y-intercept. I guess I should have defined the variables, although I think they kind of did, didn't they? Yeah. All right. Final question. Interpret the slope and y-intercept in context of the problem. Okay, so let's take a look. Our slope is 1.9. So that's 1.9 days, right? So our slope, so the context is as the trip duration increases by 1 day, the average or mean luggage weight increases by 1.9 pounds. Oh, I said 1.9 days earlier. Sorry, I meant it's 1.9 times the number of days. Okay, that's our slope. Let's do our y-intercept. It's 40.5. Okay, this one's a little weird in that that means we would be plugging in 0 for x, so we would have a 0-day cross-country trip, which again doesn't really make sense. So it's not necessarily an attainable thing, but it still has a meaning. The meaning would be you basically are going to have a minimum, a starting amount on average of 40.5 pounds of luggage, and then you add 1.9 pounds per day of trip duration, right? So for a 0-day trip, we would predict a luggage weight of 40.5 pounds on average. Okay. Again, it's not attainable, but that's what it means. Okay, that seems like a fairly quick, easy special problem. Notice they didn't ask us to do any predictions. That's what we will be doing in chapter 14. We'll be going back, doing predictions, but instead of giving single point values, we will be giving intervals for our predictions that we use our regression equations to make. So that's something to look forward to. And guess what? After chapter 14, you're ready for the AP exam. All right, thanks for watching. And if you haven't taken your Chapter 13 test yet, good luck.